Hmm. Okay. Good evening, friends. So today topic is aerosols. So friends, June 27th, I completed the biological products. 1 mark is completed out of 125 bits. Next 28th, I completed the suppositories. 1 to 2 bits completed. 29th, I completed the capsules. 1 bit completed. Today I want to complete aerosols. In every year, GPAT examination and NIPER examination, 2 to 3 bits from aerosols. Don't consider it is a single topic. Here I will just touch the rheology part and packing materials also. That's why. So the density of this chapter is 2 to 3 bits. So I will utilize your 2 hours valuable time and I will provide the strength to attempt the 2 bits from aerosols in GPAT examination, NIPER examination, and many government recruitment examination. For this chapter also, no need to refer any books. So the matter in the slides enough to attempt the aerosol bits. Okay. Myself is Venkatrao Mannem, pharmacy officer from Jharkhand state. So the pattern of my lecture is first one, I talk about introduction. Second one, basic aerosol technology, means what are the basic components present in aerosol system. Third one is we talk about evaluation of aerosols. Fourth one, we talk about previous questions. With this, the chapter will complete. Okay, first one, introduction. In introduction, definitions and some important points regarding aerosols. Second, basic aerosol technology, means what are the basic components present in every aerosol system. Third heading, evaluation of aerosols. Fourth one is solving the previous questions. Okay, so first I will start the introduction. So what is aerosol? So aerosol is a fine dispersion of solid or liquid distributed in air, where the particle size or droplet size, if we consider it is a solid, then you call it as particle. If we take it is a liquid, then you call it as a droplet. Okay. So where the particle or droplet size must be less than 50 microns. So solid distributed in air is called as aerosol. ORR. O means R. Liquid droplets distributed in air is called as aerosols. So solid particle distributed in air is called as aerosol, or liquid droplet distributed in air also called as aerosol. So this particle size or the liquid droplets size must be always less than 50 micron. First of all, you take the solute. First of all, you take the solvent. Here I am taking the solvent water. Next, dissolve the solute. I am taking the salt. Okay, salt, sodium chloride. So I am dissolving 1 gram of sodium chloride. Before dissolving into water, the powder can be absorbed with naked eye. After dissolving the sodium chloride into water, what happens? Solute dissolved in solvent form a solution. After formation of solution, the solute particles cannot be absorbed with naked eye. Why? Because the particles are widely distributed throughout the water. That's why the distribution unable to see by naked eye. Okay, that's why the uniform distribution of solute in a solvent is known as dispersion. Okay, sometimes that is known as a solution, suspension, emulsion. Everyone is comes under dispersion. Okay, solute dissolved in solvent form a solution. In this solution, solute can uniformly distributed throughout the solvent. Then this mixture is referred as dispersion, and the solute sometimes referred as dispersed phase, and the solvent sometimes referred as dispersion medium. Okay, so that's why every dispersion containing minimum two components, one is called as solute, another one is called as solvent. Here also aerosol is a dispersion, means here also it containing two phases, two components. One is solute, another one is solvent. What is the solvent phase in aerosol? That is the solvent here is air. The solvent is air. Whereas what is the solute in aerosol? That is either solid particle or liquid droplet. The solid particle uniformly distributed in air is called as aerosol, or are liquid droplets distributed in air also called as aerosol. That's why the conclusion is every dispersion containing minimum two components. One component is uniformly distributed throughout the other component. After completion of dispersion, after formation of a dispersion, the particle size must be reduced to less than 50 microns. Okay, if it is 50, it is 50 or greater than 50 micron, this particle is observed by naked eye. Observed by naked eye. So observed by naked eye. Once you observe with the naked eye, what happens? Once you observe with the naked eye, so that particles cannot be considerable, because once you observe any droplets, oil droplets, or any insoluble solid particle that is observed with the naked eye, tell me, is it preferable? No, because that particles, that visible particles or visible droplets are considered as a foreign particles or foreign droplets that cannot be acceptable by the consumer. That's why, so in any dispersion, in every dispersion, we can't see a solid particles or liquid droplet. If we see, then that our dosage form is not acceptable. That's why which particle size we can observe with the naked eye, that is having particle size of 50 micron or greater than 50 micron. These particles are visible. These particles are observed with naked eye. Okay, so visible particles cannot be acceptable in a dispersion. Okay, so in 2010 GPAT, they asked that what is the particle size, what is the particle size observed by naked eye. This is the eye. Okay, I am not that much artist. Okay, so please understand. Okay, this is the eye. What is the lowest particle size observed by naked eye under illuminated area? Under illuminated area means morning time or under light. Okay, that is called as illuminated area, under the light. Okay, that is 50 micron or greater than 50 micron. This is the question asked in 2010 GPAT examination. Once again, the smallest particle observed by naked eye under illuminated area is 50 micron or greater than 50 micron. If it is less than 50 micron, it is not observed by naked eye. That's why this invisible particles only allowed in a dispersion. It may be aerosol, or it may be emulsion, it may be a suspension. Okay, so it may be a solution. Okay, but in solution or suspension or in emulsion, there is no visible particles. If any presence of visible particle, then the dosage form is not acceptable. Okay, the final conclusion is, with the eye, we can observe a smallest particle size is 50 micron and greater than 50 micron. Okay, but we cannot observe with the naked eye, that is less than 50 micron. These particles only preferable in every pharmaceutical liquid dosage forms. Okay, with this definition is completed. In aerosol, the solvent phase is occupied by the air, whereas the solute phase sometimes occupied by the solid and sometimes occupied by the liquid. If it is a solid or if it is a liquid, but their particle size or liquid droplet size is always less than 50 microns. Next, sir, why are you stressing about particle size in aerosols? Because there is an importance for particle size in especially inhalation aerosols. What is the importance of particle size in inhalation aerosols? Friends, observe, once you inhale a drug, what happens? First, it enter into the mucous membrane of mouth or nose, because sometimes you administer through mouth route or sometimes you can take through nose. Okay, that's why once the drug enter into the mouth or nose, first this drug particle, this green color particle is drug particle. So this is the green color particle is a drug particle. First, it can touch with the membrane, mucous membrane. Next, that is called as a deposition. The particle, once you inhale a drug particle, either through mouth or through nose, the particle first touch with the mucous membrane. That is called as deposition. Next, pass through the membrane called as absorption, and enter into the blood is called as bioavailability. Once again, friends, once you inhale a drug, the drug particle touch with the mucous membrane called as deposition. Next, cross the membrane called as absorption, and enter into blood is called as bioavailability. Amount of drug enter into blood is called as bioavailability. The process of crossing of biological membranes is called as absorption. So before bioavailability, first the drug must cross the membrane called as absorption. Before absorption, first the drug must be deposited. That's the sequential steps. The sequential steps in a bioavailability is first deposition, second absorption, third, bioavailability. Then only the drug can show its systemic activity. Whenever the drug enter into blood, then only it can show its systemic activity. If the drug cannot enter into blood, just it can stick to the mucous membrane, just deposited on the mucous membrane, then it can show its local activity. That's why every drug particle having, sometimes it can show local activity by deposition on the mucous membrane, or it can show systemic activity by enter into blood. Okay, next. So once next, the drug may enter into mouth or nose. Next, pharynx. Next, larynx. Next, trachea. Next, bronchi. Bronchi again divided into bronchioles. The first bronchiole is the terminal bronchiole. The terminal bronchiole again divided into respiratory bronchiole. The respiratory bronchiole again divided into alveolar ducts. So these are called as alveolar ducts. Duct means pipe-like structure, like a water pipe-like structure. Okay, duct means water pipe-like structure. Across the alveolar ducts, an alveolar sac is present. This is called as alveolar sac. Alveolar sac. From this alveolar sac, an alveoli can be produced. The produced alveoli deposited across the alveolar ducts. Okay, this is the respiratory tract. Once again, once the drug is inhaled, that will enter into the mouth or nose, followed by pharynx, followed by larynx, trachea, bronchi. Next, bronchi divided into terminal bronchioles. Next, terminal bronchioles again divided into respiratory bronchiole. Respiratory bronchiole again divided into alveolar ducts. Across the alveolar ducts, there is a alveolar sac is present. From this alveolar sac, there is a alveoli can be generated. The generated alveoli deposited across the alveolar ducts. That means pipe-like structure. Then we can observe which particles can deposited in which area. Okay. So large particles means greater than 10 microns, Larger particles can enter into the mouth. So these larger particles can deposited or exhaled, either deposited or exhaled only at a mouth or nose or pharynx or larynx. These three regions, these three tissues collectively referred as upper airways, because it's the upper part of respiratory tract. Which particles can able to deposit in upper airways? That particle size having greater than 10 micron. So don't consider greater than 10 means 20, 30, 40, 50. So there is no chance of 50 micron particle, because that 50 micron particles are visible. That's why it cannot be acceptable. That's why less than 50. So all particles cannot be deposited, only just a small 10.1, 10.2 can only deposited. Then the remaining will be exhaled by reflex mechanisms like coughing or sneezing. Because so once any dust particle enter into the tissues, is it deposited in the tissue? No, it rapidly eliminated out by reflex mechanisms like coughing or sneezing. That's why this greater than 10 micron particle will either deposit or exhaled from these tissues. Okay, that's why it can deposit or it can exhale from this tissue. But this greater than 10 micron particle cannot enter into trachea, That's why this greater than 10 micron particles can be either deposit or exhaled only in these three tissues, which is the three tissues are collectively referred as upper airways. So always don't no need to refer mouth, pharynx, larynx. Just you can say it as upper airways. Okay. In interview, whenever they will ask larger particles can deposit in which area of respiratory tract, means you can simply say it is upper airways. Okay, that's why. What is the meaning for large particle size having greater than 10 microns? Okay, that's why this greater than 10 micron particle either show local activity or it can enter into blood only at upper airways. It confined to upper airways. This greater than 10 micron particles selective seats are mouth or nose, pharynx or larynx. Okay, next, moderate particles. Moderate particle means already greater than 10 is completed. Next up, 5 to 10 micron. 5 to 10, because greater than 10 is already completed. 5 to 10. This 5 to 10 micron particles can deposit in, so larynx completed. Next, trachea, bronchi, terminal bronchiole. Okay, so these three tissues, trachea, trachea, next bronchi, next terminal bronchiole. These three tissues are collectively called as conducting airways. So in conducting airways, which particles can be either deposit or it can enter into blood, that is 5 to 10 microns. But this 5 to 10 micron particle never enter into the respiratory bronchiole. It can be confined to the conducting airways. It can either deposit or it can enter into blood only in this region. Okay, next up. So terminal bronchiole also completed. Next, smaller particles whose particle size is 2 to 5 microns can be deposited in lower airways. Lower airways. What is lower airways? After terminal bronchiole, next respiratory bronchiole, next alveolar ducts, next alveolar sac, next alveoli. Okay, what is alveolar sac? This is one alveoli, and this is one more alveoli, and this is one more alveoli. If two or more alveoli share common opening, when two or more alveoli share common opening, so 1, 2, 3. So this is the common opening. Okay. So when two or more alveoli share common opening known as alveolar sac, from which an alveoli can be generated. Once the alveoli is generated, the generated alveoli deposited across the alveolar ducts. Okay. So once again, what is alveolar sac? When two or more alveoli share common opening known as alveolar sac. What is the use for this alveolar sac? From alveolar sac, the alveoli can be generated. Okay. Next. That's why this is the lower part of the respiratory tract or deeper part of the respiratory tract. That's why it is called as lower airways. Another name is deeper airways. That's why. So the smaller particle whose dimension is 2 to 5 micron, it can be deposited in the lower airways. So lower airways comprises of respiratory bronchiole, next alveolar ducts, alveolar sac, finally alveoli. These tissues are collectively referred as lower airways. Which particles can deposit or enter into blood? That is 2 to 5 micron particles. Okay. Next, very smaller particles, that is less than 2 already completed. That's why less than 2 micron. Okay. So less than 2 micron particles can be deposited in. Okay. Already respiratory tract is completed. Already there is no seats in the cinema theater. If we enter into the theater, already all seats are filled up. what could you do? What could you do? So you can, this is the way to enter. So you can observe and left side and right side. Okay. So if there is no, any chairs are not available to sit, then immediately you can return back, because you cannot sit on floor. That's why you can return back. That's why this less than 2 micron particles also easily passes through the deeper airways, easily passes through the lower airways. It fastly, rapidly enter into the lower airways, and that much fast it can be immediately written back. Immediately it will be written back. Why, sir? Because there is no seats to sit. That's why the less than 2 micron particles having no site, no tissue to deposit. That's why this less than 2 micron particles cannot deposit in respiratory tract. That's why once it is not deposited, it cannot be absorbed, it cannot enter into blood. That's why it having no biological activity, no therapeutic activity. That's why these particles having no importance in inhalation aerosols, because these particles easily pass through the deeper airways, lower airways, and easily exit from the respiratory tract. Okay, it enters with the inhaled air, it enter with inhaled air and exit with exhaled air. That's why it always associated with the air but not with the tissues. So which particle can show activity? That particle always do friendship with the tissue, not with the air. But this particle, very smaller particle, always enter with the air and exit with the air. That's why it enter with inhaled air and exit with exhaled air. That's why this type of particles are commonly pronounced in aerosol technology as aerodynamic diameter. Aerodynamic diameter. Aerodynamic diameter. What is the meaning for aerodynamic diameter? Dynamic diameter means particle size, okay, which always associated with the air. That's why. So, friends, you know that if you inhale the air, tell me, is it air molecules can deposit in your tissues? No. That's why that air can easily pass, enter into the deeper air, lower airways, and easily exited. Okay, that's why likewise these particles also associated with air. It enter with the air and exit with the air. So enter with inhaled air, exit with exhaled air. That's why there is no deposition. That's why there is no therapeutic activity. That's why in interview, if anybody will ask which particles are not recommended in inhalation aerosols, that is aerodynamic diameter. What is the size? That is less than 2 micron. Okay, why it cannot deposited? Because there is no chairs. Okay, there is no seat in respiratory tract. Now, friends, I am asking one question, that is, what is the particle size range in inhalation aerosols? So we take only particles that having the ability to deposit. That's why less than 2 cannot deposit. That's why the inhalation aerosol, the particle size start with minimum is 2 micron, maximum is greater than 10 micron. Maximum 10, greater than 10 means you consider it is less than 50 micron. That's why the particle size in inhalation aerosols always range between 2 microns to less than 50 microns. Less than 50 micron. This is the called as particle size distribution in inhalation aerosol. Okay, distribution. What is the meaning for distribution? That is the smallest particle and largest particle. That's why if you randomly collect the inhalation aerosol product and check the particles, their size must be in between 2 to less than 50 micron. Okay, once again, friends, what is the importance of particle size? So particle size can decide the site of deposition. Once I say the particle size, for example, I am saying I am developing an aerosol system. I am developing an aerosol system. I am developing an aerosol system. So here I am developing an aerosol system which containing the particle size, for example, which containing the particle size 7 microns. Now tell me, so if this aerosol product containing 7 micron particle, imagine it can deposit in which area of respiratory tract. 7 micron means yes, in between 5 to 10 micron. Yes, 7 micron means in between 5 to 10 micron. That's why yes, there is a possibility or there is a chance of deposition of the 7 micron particle in conducting airways. That's why it can show its local activity, or it can enter into blood only in conducting airways. Okay, for example, if it containing the 3 micron particle, then you can imagine this 3 micron particle can deposit in which area of respiratory tract? Yes, lower airways, because 2 to 5 micron means 3 lies in between 2 to 5 micron. That's once I will say the particle size, immediately you decide where it can be deposited in the respiratory tract. Respiratory tract containing how many chairs? 3 chairs. One chair, first chair is called as upper airways. Second chair is called as conducting airways. Third chair is called as lower airways. First chair is reserved for which person? Person having the size greater than 10 micron. Second chair is already reserved for which person? 5 to 10 micron size particle. Okay. Third chair is reserved for person having the size 2 to 5 micron. Okay, but which person having no chair? That is very smaller particle. That's once I will say the particle size, immediately you decide where it can sit. Where it can sit. That's why the importance of particle size in inhalation aerosol is it can determine the site of deposition, where it can be deposited. That is decided by only particle sizes. Okay, without knowing the particle size, we can't say where it can be deposited. Okay. With this, the importance of particle size is completed. First definition is completed. Second, importance of particle size. What is the particle size distribution in inhalation aerosols? That is a 2 to 50 micron, less than 50 microns. Okay, don't say 50 micron, you can say less than 50 micron. Why you can't say 50 micron? Because that is observed by naked eye. Any particle observed by naked eye is not considerable, because that is considered as a foreign particle. Okay, we feel it is a dangerous particle. Okay, next up. This is the importance of particle size. Friends, now tell me, so once I am giving randomly, I am giving the aerosol system to you in your hand. In your hand. I am not mentioning the particle size. I am not mentioning the particle size. On the label, on this label, I am not mentioning the particle size. Once I mention the particle size, immediately you decide where it can be deposited. But here, I am not mentioning the particle size on the label. Now tell me, so here, the particles in this product can deposited in which area? In which area? That is, that particle size in inhalation aerosols can be determined by one is cascade impactor, another one is light scattered decay. Once again, cascade impactor, another one is light scattered decay. That's why the particle size in inhalation aerosols can be determined by using cascade impactor or light scattered decay. Okay, so 3 times asked question in previous gate paper. Which one of the following instrument used to measure the particle size in inhalation aerosol? That is cascade impactor and light scattered decay. Sir, how could you say particle size is greater than 10 micron, 5 to 10 micron, 2 to 5 micron, less than 2 micron? How could you say? By using cascade impactor or light scatter decay. By using this instrument only, we can calculate the particle size. Once you calculate the particle size, then only we can say where it can be deposited, where it can be sit, where it can show its activity. Okay, with this, the introduction is completed. The introduction is completed. So 3 parts: upper airways, conducting airways, lower airways. Next, friends, lung structure. Once you draw the lung structure, means you can draw lung structure like this. Lung structure is like this. This is the lung structure. Okay. Generally, you can write like this. Okay. Now tell me, this is the lungs means. So how many? So actually, respiratory tract, we consider respiratory tract into 3 parts. Okay. One is upper airways, conducting airways, and lower airways. Now, imagine this lungs means you consider which parts? Lungs means, L means lungs is equal to, tell me which parts are combinedly called it as lungs. That is, one is the conducting airways plus another one is the lower airways. That's why lower airways. Lower airways. That's why One is conducting airways, another one is the lower airways. This is called as lungs. Okay, now tell me which particle size can distribute in entire lungs. That is, so here in lower airways, what is the smallest particle? 2 micron. In conducting areas, what is the largest particle? 10 micron. That's why 2 2 in this lungs. This is called as lungs. So which particles can able to deposit? That is 2 2 2 2 10 microns. Okay, any device which deliver the drug especially into lungs is known as metered dose inhaler. Metered dose inhaler. Simply it is an aerosol container. Okay, but what is the specificity? It can selectively deliver the drug into lungs. What is lungs? Lungs means is the conducting airways and lower airways collectively called as lungs. Which particle size can deposited in lungs? 2 to 10 micron. Any device which deliver the drug into lungs, device deliver the drug into lungs is known as metered dose inhaler. Okay, in 2019, Central Drug Control Officer Rajasthan, they asked that what is the particle size distribution in metered dose inhaler? Metered dose inhaler, that is a 2 to 10 microns. 2 to 10 microns. Why? Because so this 2 to 10 microns only deposited in lungs. Who can deliver this 2 to 10 microns into lungs? That device is called as a metered dose inhaler. Always we are using a metered dose inhaler. For example, asthma patient, which are they are using an aerosol container, small aerosol container. That small aerosol container, upon pressing, what happens? That drug directly enter into the lungs, directly forcefully introduced into the lungs. That aerosol container is known as metered dose inhaler. Once again, metered dose inhaler is a device that specifically deliver the drug into lungs. Okay, the particle size distribution in metered dose inhaler is 2 to 10 microns. Next, second heading is basic aerosol technology. Basic aerosol technology. So, what are the basic components present in aerosol technology, aerosol system? Okay, the meaning for heading is basic aerosol technology means what are the basic components required to construct the aerosol system. So, friends, so which is minimum components required? One is container. Without container, we can't design the aerosol system. Okay, first component. Second component, liquid phase. In liquid phase, what is liquid phase? Is containing propellant or propellants, because sometimes we take only one propellant, in sometimes we take mixture of propellant. That's why I'm writing it as propellant or propellants. Plus or minus means with, plus means with, minus means without active ingredient, because in deodorants there is no active ingredient, whereas in case of medicated aerosol there is a presence of active ingredient. That's why, so container is essential, liquid phase is essential. Liquid phase means propellant with or without active ingredient. Next, because this propellant only supply this vapor. Okay, the role of propellant is supply the vapor. Thus, vapor only exert pressure on the surface of this liquid and walls of the container. Due to this pressure, okay, the liquid will be forcefully ejected out. The liquid will forcefully ejected out. That's the important component in aerosol is propellant. Okay, one specific component that is absorbed only in aerosol but not in any other pharmaceutical dosage form is the propellant. Okay, so container in emulsions or packing of emulsion, suspension or parenterals, we use the container. Okay, but what is the specific component present only in aerosol is the propellant. What is the importance of this propellant? They just supply the vapor. Due to this vapor, only drug product is forcefully ejected out. Why force is required? Because this drug will be introduced into the lungs. To move it deeper to the lungs, it needs more pressure. Okay, next, third point. Third component is valves. Third component is the valves. What is a valve? A small orifice, a small hole is called as orifice. In aerosol system, any component containing a small hole, that component is referred as a valve. That component comes under valve. Here you observe activator, it containing small hole. Okay, that's why it is called as activator valve. Next, this is called as stem. The stem also containing small hole. That's why it is also called as stem valve. Next, this is called as ferrule, because which join these valves with the container. Okay, that's why this is a ferrule. So the shape appears like a cup shape. Observe here. This is the cup. That's what is called as ferrule or mounting cup. What is the meaning for ferrule? Which join outer component with the container. Outer components with the container. Okay. So by seeing the shape, it is also named as mounting cup. By observing the function, ferrule. By seeing the structure, mounting cup. Okay. Next one is, this is called as valve housing or valve body. Why it is called as valve housing, valve body? Observe inside this chamber. Which component in sleeping mode? That is a stem. Only stem can be placed in this chamber. That's why it is a house, guest house for stem. That's why it take rest in this chamber. Okay, that's why. So it is a house or body for stem valve. Okay, because in this chamber there is a stem is enclosed. Okay. Next one is, inside the chamber two components are there, but these two components are not called as a valve. Okay, but valve is nothing but valve housing or valve body. But inside this chamber, there is a two components are present. One is gasket, another one is spring. So gasket prevent the leakage, whereas spring can push the stem. Okay. If we press on top, okay, who will press from bottom means that is a spring. Okay. Next one is dip tube. This is the dip tube. Is responsible to suck the liquid from container and send the liquid to chamber. Which chamber? Valve housing, valve body. Okay, that's why these all containing the small orifice. Activator containing small orifice, stem containing small orifice, valve housing or valve body also containing small orifice. Next, dip tube also containing small orifice. That's why these five components: 1, 2, 3, 4, 5. These five components are pronounced as valve. Why? Because it containing small orifice. Okay, that's what is called as valve. Without these three components, we can't construct the aerosol container. First one, container. Second one, liquid phase. In liquid phase, which is important component, propellant. That's why. So here I want to talk about container. Second, I want to talk about propellant. Third, I want to talk about valves. Okay. Next, this is called as basic aerosol technology. Basic components present in aerosol system, that are every aerosol system containing three basic components. One is container, second one is liquid phase, third one is valves. So what is liquid phase? Is a propellant or propellants with or without active ingredient. Second, what are valves? A component containing small orifice. How many valves are present? 5. One is activator, second stem, third ferrule, also called as mounting cup. Next, fourth one, valve housing or valve body. Fifth one, dip tube. Okay, next. First, I want to talk about containers. Okay, so which materials are used to construct the container? Simply metals and otherwise glass. Okay, metals and glass. The metals can withstand a pressure of 140 to 180 pounds per square inch gauge at 130 Fahrenheit. This is the most important point in container concept. Before going into the examination hall, just you check this one. Okay, so metals. So why I'm saying metal or metals? Sometimes we use only one metal. Sometimes we use alloys. What is alloys? Mixture of metals. That's why I'm using the word metal or metals. Okay. So metal can withstand a pressure because aerosol is a pressurized product. Okay. Who can supply the pressure? Propellant can supply the pressure. That's why that pressure will be withstanded by the container. That containers only used to pack the aerosol product. Okay, that's why here pressure withstanding of container is very important point. We can't use the plastic because once you use the plastic, that will be bulged out and immediately break down. Okay, that's why we use only metal or glass. Okay. So metal can withstand how much pressure? 140 to 180 pounds per square inch gauge, which is measured at 130 Fahrenheit. You know that relation between pressure and temperature. So according to Boyle's law, pressure is directly proportional to temperature. As the temperature increases, pressure automatically increases. That's why we don't say only pressure. Okay, you can say pressure where it is measured. Okay, that's why here 140 to 180 pounds per square inch pressure, which is measured at 130 Fahrenheit. Okay, that is withstanded by metal. That metal only used for the packing of aerosol product. Okay, so sir, why we are using Fahrenheit? Because aerosol is an ancient system. Ancient system. It is introduced in 1942. Okay, Second World War. Okay, so first time introduced aerosol systems are nothing but bug system. Okay, so because the soldiers during war, the soldiers move across the forest, so where the mosquito will bite. That's why at that time, so many soldiers will die due to the malaria. Okay, so due to the mosquito bites. That's why, so at that time they first introduced the smoke bugs. Okay, that's why that is referred nowadays, you referred as a aerosol product. Okay, that's why, so that is the stepping stone to develop this aerosol system. Okay, like now that is used to deliver the drug efficiently into lungs. Okay, that's why every unit will be in an imperial system, because the units used in ancient days called as imperial measurements. Imperial measurements, whereas the measurements used in current days called as metric measurements. That's why you go and check in any standard textbook. Okay, in entire aerosol chapter, they never mention the degree Celsius. They always mention the degree Fahrenheit. Okay, and pressure unit pounds per square inch gauge. Okay, atmospheres, not in bar, not in torr. They always represent in a pounds per square inch, because pounds per square inch is the unit for pressure in imperial system. Okay, once again, metals. Which metals are used? That metal must withstand a pressure of 140 to 180 pounds per square inch gauge, which is measured at 130 Fahrenheit. This is the most important point in aerosol containers. Okay, next, what is the problem with the containers? What is the problem with the containers? So observe, this is the metallic container. So if this aerosol product, if the aerosol product containing any water, okay, moisture, that moisture will touch with internal walls of the metal, okay, internal surface of the metal. Once the water touch with the metal, observe H2O. Here there is a positive presence of oxygen. There is a presence of oxygen. Or in this product, if there is any acid moiety, H2SO4, SO4O, oxygen is present. Okay, that's why. So if any air is present, O2 is present. That's why this oxygen will cause the oxidation of the metal surfaces. The oxidation of metal surface is called as corrosion. That's why there is a formation of rust across the inner walls of the container. Once a rust is formed, what happens? Some rust will be dropped into the aerosol product. Once you inhale, what happens? This rust entirely introduced into your lungs. Otherwise, it can block the valves also. That's why this is the major drawback for metallic containers. Sir, why metallic containers are prone to corrosion? Due to presence of moisture in the aerosol product, or any acid moiety is present in the aerosol product, or any air. Air means oxygen, because air means group of gases. In that gas which is dangerous, oxygen is the dangerous. That's why sometimes in pharmaceutical doses form we pronounce air means immediately you can consider it is a oxygen, because so most of the pharmaceutical manufacturers struggle with the oxygen, because that only cause the oxidation. That's why here this water touch with metal surface and will cause the corrosion, also called as rust. Okay, next. That's why how can you prevent? That's why as it is, we cannot release the product into the market. You have to take preliminary precaution. First, you have to know. So one problem means immediately you have to try to rectify that problem. Then only you can market the product. Okay, that's why how can you reduce this corrosion property of the metal surface? We can reduce but not prevent. Okay, how can you reduce? That is by coating with the epoxy or vinyl polymer. Epoxy or vinyl polymer. This epoxy or vinyl polymer is a water repellent, hydrophobic polymer. That's why once water try to touch with the metal surface, but before metal surface there is a protective coat is there, epoxy or a vinyl polymer that can aid the water. That's why once water approach the polymer, immediately it will be repelled out. That's why water cannot touch with the metal surface. That's why there is a less possibility of corrosion. That's why the protection of metal surface, the protection of metal surface is known as passivation. The protection of metal surface is known as passivation in metallurgy. In metallurgy, they always use one word that is passivation. Recently, in some competitive examination, they are using this word passivation. What is the meaning for passivation? Protection of metal surface. Now tell me, you remove that protection of metal surface, just place the passivation. How can you passivate the metal surface? How can you protect the metal surface? Just by coating with epoxy or vinyl polymer, which is a water repellent. That's what acts as a screen. That screen always repel water. That's why water cannot touch with the metal surface. Thereby, the corrosion will be decreases. 3 points, friends. First one is, what is the important property for a metal used in the packing of aerosol product, that must withstand a pressure of 140 to 180 pounds per square inch gauge measured at 130 Fahrenheit. Second point is disadvantage. Corrosion is the major drawback. How can you prevent? By coating. Not prevent, how can you reduce? How can you reduce? That is by applying the epoxy or vinyl polymer. Second one is the glass. So glass withstand a pressure of just less than 18 pounds per square inch gauge. That's why, friends. So here it cannot withstand the highest pressure, because if we increase the pressure, what happened? The glass will be burst out. Thereby it will cause the environmental hazards. That's why. So how much pressure is standard by the glass? Just 10% of the 10% of the pressure withstanded by metal. Just 10% of pressure withstanded by the metal, because it is 180. This is just 18, means this is the 10% of the pressure with the standard by metal. That's why it is not used for inhalation purpose. Why? Because in inhalation you have to deliver the drug into deeper airways, means lungs. To deliver into lungs, it needs more pressure. So that much pressure is not standard by glass. That's why glass is limited to only cosmetics, but not inhalation aerosols. Okay, that's why. So in a examination, they always ask about only metal. Okay, if they not ask metallic container, means immediately you choose 140 to 180, because out of these two, as a so with you having any small knowledge, immediately you can prefer the metal or glass for inhalation aerosol. Just metal only you can prefer. That's why aerosol container means immediately you can imagine that is a metal. Okay. Next, this glass is some used for only cosmetic purpose. Okay, deodorants purpose. Okay, likewise. Next, what is the problem with the glass? What is the problem with the glass? So this is the glass. What happened once this product containing moisture, water, that water touch with the glass surface. Once it touch with the glass surface, that alkali will be released into the product. Once it released into the product, what happened? Alkali means base. The product pH will be increases. Okay, any change in color, flavor, anything. So then the product is called as unstable. Okay, that's why here once the water touch with the glass surface, water touch with the glass surface, water touch with glass surface, that alkali will be released from glass walls into the product. This is called as leaching. Okay, what is the leaching? Is the process of release of alkali. The process of release of alkali from glass walls when water touch with the glass surface. Next, how can you reduce the leaching property? As it is same, by coating with the silicon fluid. Here not I am applying polymer, here I am applying silicon fluid. Chemically silicon fluid is poly dimethyl siloxane. Once again, poly dimethyl siloxane, which is a water as well as oil repellent. Already I told you in surgicals. Okay, so water as well as oil repellent. Once you apply this silicon fluid on inner walls of glass, it can always repel the water. Thereby water cannot touch with the glass surface. That's why the leaching tendency also decreases. Sir, why the alkali is released from the glass surface? Okay, because friends, glass means this is a silicon dioxide, silica, also called as quartz, simply called as glass. Okay, to import the color to glass, we generally add the metal oxides. For example, to import the color to this glass means silica. Okay, so for example, if we add the lead oxide, yes, lead is a metal, lead oxide, it will impart the transparency, clarity, clarity. The clarity of glass is mainly because of transparency of glass is mainly because of presence of lead oxide. Next, iron oxide. This iron oxide is responsible for brown color of the glass. Brown color glass also called as amber color glass. Okay, amber color glass. These are two widely used glasses in pharmaceutical dosage form. In some cases, cosmetics we use the. This is the cobalt oxide. Cobalt oxide. Cobalt oxide impart the blue color to the glass. Blue color to the glass. Whereas chromium oxide, Cr2O3, Cr2O3, responsible for green color of the glass. Green color to the glass. That's why, sir, why you are adding the metal oxides? These metal oxides are bases. Metal oxides are bases. Base means alkalis, which love water, which always love water. Once water touch with the glass surface, the walls containing this all metal oxide. In case of transparent glass, lead oxide is awaiting to attract with the water, to interact with the water. In terms of amber color glass, ferric oxide will awaiting on the glass walls to touch, to interact with water. Next, in blue color glass, cobalt oxide. In green color glass, chromium oxide. Once water touch with the glass walls, immediately this all metal oxide jump into the water. Thereby, the product pH will be drastically increased. Thereby, the product becomes unstable. Okay, that's once again the transparency of clear glass is mainly because of lead. The brown color of the glass is mainly because of ferric oxide. The blue color of the glass is due to the cobalt oxide, whereas the green color is due to the chromic oxide. Okay, next. Then, so friends, the common disadvantage is the common disadvantage is that common disadvantage is any aerosol product that containing moisture, then only we can observe corrosion in case of metal, leaching in case of glass. That's why. So how could you know whether the product containing water or not? Okay, that can be measured by using Karl Fischer titration and gas chromatography. Because once you know water is present or not, once water is present or not, if more amount of water is present, immediately you try to eliminate out. Otherwise, what happens? Metal will prone to corrosion, glass will prone to leaching. Even you apply this protective walls, but you take the precaution to reduce the moisture content in the aerosol product. How could I know, sir, amount of water present in the aerosol product? That is by using Karl Fischer titration and gas chromatography. If one unknown aerosol is given to you, immediately you have to check. Before packing, you have to check whether the product containing water or not. How? By using Karl Fischer titration or gas chromatography. Okay, so this is called as evaluation. Okay, in the first introduction, you are evaluating the particle size. What is the particle size in that aerosol product? How can you evaluate? By using cascade impact or light scatter and decay. Next, whether the product containing moisture or not, how can you evaluate? That is by using Karl Fischer titration or gas chromatography. Okay, with this the container is completed. The first component in basic aerosol technology is completed. Okay, so after completion of this explanation, you have to remember the most important point is the pressure withstanded by metallic container. This is a 3 times asked question in previous GPAT and GATE papers. Next, propellants. Propellants. So in liquid phase, the most important, because here I want to talk about only common components in aerosol system. Okay, liquid phase containing propellant with or without active ingredient. Active ingredient is variable component, but I am talking about only common component. Without that components, we can't say it is aerosol system. That is the propellant. That's why I'm talking about in liquid phase. I'm talking about propellants. Okay, what is propellant? Ent means a substance. Ent means substance which cause expulsion of. Propel means expulsion. Expulsion. Propel means expulsion. A substance used to expel the aerosol product is known as propellant. How it can expel the aerosol product? By supplying the pressure. By supplying the pressure. That's why the duty of propellant is only supply the pressure. Due to this pressure, the aerosol product forcefully ejected out. Okay, next. These propellants are available in market in two types. One is liquefied gases, another one is compressed gas. Function is only one that can provide the pressure. Okay, then why sir it is existed in liquefied gas and compressed gases? Here the difference is these two differ only how this propellants fill it into the container, how it can fill it into the container. First here observe the gas is first converted to liquid, and this liquid only poured into the container. Liquid is poured into the container. Pour into the container. That's what is called as liquefied gases. Once again, why it is named as liquefied gases? Before pouring the propellant into the container, first you have to convert the gas into liquid. Why? Because here the common word is gas. Common word is gas. That's why the propellants are in gaseous state. Sometimes the gases as it is can be filled into the container. In sometimes the gas is first converted to liquid and the liquid can be poured into the container. That's why here in this type, the first you take the gas. That gas will be converted to liquid. How can you convert gas to liquid? By decreasing the temperature or by increasing the temperature? Yes, by decreasing the temperature. At which temperature? The gas propellants are completely converted to liquid. That is minus 30 degree Fahrenheit or minus 40 degree Fahrenheit. This is very, very important. Two times asked question in the GPAT examination. The temperature. Okay, minus 30 degree Fahrenheit or minus 40 degree Fahrenheit. You know that why they are indicated as Fahrenheit? Because it is an ancient system. So you can easily remember 30 and 40. So to remember this minus sign, okay, they given the name cold. Okay, cold means chilling. Chilling means below 0 degree. That's why. So to represent this minus, to remember this minus, they given the name cold filling method. Liquefied gases can be filled into container by using cold filling method. So in cold filling method, what is the temperature maintained? Minus 30 degree Fahrenheit or minus 40 degree Fahrenheit. At this temperature, gases are condensed to liquid. That liquid can be poured into the container. Okay, so this is the filling method. Okay, liquefied gas is always filled into the container using cold filling method. What is the temperature maintained? Minus 30 degree Fahrenheit or minus 40 degree Fahrenheit. Okay, next, compressed gas propellant. Here the gases are directly compressed into the container. Directly compressed into the container by applying compressional pressures. Compressional pressures, like in a sodas. Compressional pressures in cool drinks. Compressional pressures. So in a sodas, what happened? We fill the carbon dioxide. How? By using the cylinder, okay, the gas cylinder. So that having one instrument that can forcefully compress the gas into the container. Compress the gas forcefully introduced into the container. That's what is called as compressed gas propellant. Gases are compressed into container by applying compressional pressure. So it is called as pressure filling method. Pressure filling method. Okay. So this pressure filling method used to fill the compressed gases. Okay. So next, out of these two methods, which method is most important? Cold filling method. Why? Because first you observe the advantages and disadvantages. Two products are available in market means one only having the high priority, another having the low priority. How can we decide? Based on their advantages and disadvantages. Here, what is the advantage of liquefied gases? Here, liquefied gases maintain pressure remains constant. Okay, so this is the product. This is the product you purchase from market. Okay, medical shop. This is the propellant. Okay, so after continuous usage also, if there is single droplet is present, single droplet of propellant is present inside the container, that maintains same pressure. So same pressure. That's why. So until there is a presence of single propellant droplet, it maintains constant pressure inside the container. Thereby, the product will be entirely utilized. Okay, entirely ejected out. Okay, this is the advantage of liquefied gases. But here in compressed gases, pressure decreases as the product is used. Why? Because this is the aerosol container. So So this is the propellant you consider. This is the product, aerosol product. The space above the liquid surface, the space above the liquid surface is known as air space. Is known as air space, also called as head space. This is called as air space, or also called as head space. The space above the liquid surface, which is occupied by the vapor. Which is occupied by vapor. The vapor only exert pressure. Now I am utilizing this product. I am utilizing the product. What happened? Upon pressing the activator, what happened? The product will be increased. First time, while you bring the product from the market, this is the airspace. This is the airspace. Okay, airspace is very small, very small. If the airspace is small, for example, this is the airspace. In this airspace, more amount of air will be accumulated. Means here the air will be existed in congested state. Why? Because space is less, congested state. That's what exert the more pressure in all directions. More pressure in all directions. While utilize the product, what happened? Now you utilize the product, what happened? The airspace will be increased. The airspace will be increased. As the airspace increases, what happened? As the airspace increases, the gas molecules will be expanded. The gas molecules will be expanded. This is the gas molecule. Because space is increases. Why? Because liquid product is utilizing. That's why the air molecules will be expanded. If the air molecules are expanded, the pressure will be decreases. Imagine water pipe. If we press the water pipe, the pressure is more. If we dilate the water pipe, the pressure will be decreased. Okay, that's why here the water pipe in construction mode. That's why it exerts more pressure. But here water pipe is expanded. That's why the pressure will be decreases. If the pressure is decreases, the final product cannot be forcefully ejected out. That's why some liquid will be left inside the container. That's why you observe in deodorant bottles. So at last stage, we heard some liquid sound inside the container. Even you try to press this activator, but the product cannot be ejected out. Why? Because this small amount of propellant cannot exert that much pressure to eject that final droplet. That's why some product will be left inside the container if you want to decide to use the compressed gases. So deodorant means you can leave it, okay. But in case of active medicament, within the one drop, there are several drug molecules will be present. That's why we can't leave some product inside the container. That's why. So out of these two, which having more importance, liquefied gases. Why? Because liquefied gas maintain constant pressure. Even a single droplet of propellant is present inside the container. Okay. So whereas compressed gases cannot maintain constant pressure. So tell me why liquefied gases only maintain constant pressure? Because friends, already you heard that how can you fill the liquefied gases into the container? First gas converted to liquid. That's why gas converted to liquid. Inside the container, what happened? This liquid slowly converted into gas. This gas only maintain constant pressure. Okay, you are filling gas converted to liquid poured into the container. While the product is utilized, some amount of liquid will be converted to gas. This gas only maintain constant pressure inside the container. But here, you are filling only directly gas. That's why there is no possibility of change in states. So as the product is utilized, some amount of liquid is expelled out, thereby space will be increased. This air will expanded, the pressure will be decreases. Okay. So tell me, how could I know? It maintain constant or pressure does not maintain constant? Randomly, I am giving one aerosol product to you. Okay. Tell me, here the propellants maintain constant pressure or not? How could you know? On label, I am not mentioning it is a liquefied gases or a compressed gases. Okay, so how could you know whether the propellant maintain constant pressure, does not maintain constant pressure? Okay, that is evaluated by using spray pattern test. Here, the advantage of liquefied gas and disadvantage of compressed gas is identified by using spray pattern test. Okay, so now how can I say advantage? How can I say disadvantage after performing the spray pattern test? Sir, how can you perform the spray pattern test? Friend, this is the spray pattern test. Okay, take a piece of paper. Take a piece of paper. This is the piece of paper. Coat with dye and talc. Okay, why you are coating with the talc? Because these are propellants or organic solvent. That's why upon pressing, what happens? Some solvent will be once it touch with paper. Next, after 1 second, 2 seconds, the solvent will be evaporated. Thereby, we can't draw the perfect spray pattern. Okay, that's why you have to coat the white paper with dye and talc. Okay, so here talc acts as a adsorbent. Dye give the permanent record of pattern, spray pattern. Okay, once you press that activator for fraction of second, means just to touch that activator, immediately the liquid will strike the piece of paper. Next, this solid dye particle interacts with the solvent because this propellant acts as a solvent for this dye. This dye interacts with the propellant and form a solute, interacts with solvent, form a solution. This is the solution. Once it is forming more solution, what happens? This solution drops from paper. So to prevent that dropping of solution from the piece of paper, so talc is added. This talc immediately, once solution is formed, rapidly it is absorbed by the talc. Rapidly absorbed by talc. Then we get the permanent record. This is the first time for you brought the product from medical shops. Okay, this is the first page. Next, after 1 day, next after second day, after third day, you have to spray. Then observe the records. Okay, observe here in this example. Observe this circle, large circle, diameter large. As as the product is utilized, what happened? The pattern size will be decreased. The pattern size decrease means the internal pressure will be decreases. That's why then only we can decide yes, this propellant which is present in this product not maintaining constant pressure. How could you say? By comparison the patterns. Okay, to get the permanent pattern you are using dye. Once the dye interacts with solvent, form a solution. The solution is rapidly absorbed by the talc. Okay, then we get this record. Okay, by seeing this record only we can say the propellant not maintain constant pressure or maintain constant pressure. If the circles are uniform, concentric means equal diameter, then we can say yes, the pressure inside the product is constant. The propellant maintained constant pressure inside the container. Here, this is the example. Now, friends, tell me the compressed gases can show this type of pattern. Pressure not maintained constant. This type of pattern. As the product is utilized, the pressure decreases. The pattern size will also decrease. Okay, this is the word spray pattern test. By using spray pattern test only, we can say whether the propellant maintained constant pressure or does not maintain constant pressure. Okay. With this, the first classification is completed. Major classification is completed. Here, now tell me which is most preferable for inhalation aerosol? Liquefied gas. Why? It maintain constant pressure. That's why a single droplet of the product also utilized if you use liquefied gases. But if you decide to use the compressed gases, some product will be left inside the container. Okay. Next, compressed gas is again classified into soluble gas and insoluble gas. Sir, already you told that liquefied only preferable. Yes, but even it is liquefied gas only preferable, but it is needed to learn the compressed gases also. Okay, so compressed gases again classified into water soluble gases, water insoluble gases. Water soluble compressed gas example carbon dioxide and nitrous oxide, also called as laughing gas. Okay, so in sodas we can observe the carbon dioxide which is existed in dissolved state. Next, insoluble compressed gases, nitrogen, argon, krypton, xenon, inert gases. Inert gas means the gas cannot interact with other gases in atmospheric temperature. Okay, this is the soluble water soluble compressed gases, water insoluble compressed gas. These two suffers with disadvantage, not maintain constant pressure. Okay. Next class is liquefied gases again classified into two categories. One is fluorinated, one is hydrocarbon propellant, another one is fluorinated hydrocarbon propellant. Hydrocarbon propellant means the name itself indicates the propellant containing hydrogen and carbon. Hydrogen and carbon. That's why hydrogen and carbon. Examples are propane, butane, isobutane, neobutane. Simply it is the paraffin, means alkanes, paraffins. Simply these are paraffin, saturated hydrocarbons called as paraffins, alkanes, also called as alkanes. These alkanes, examples for hydrocarbons. But already I told you, if two products are available in market, one only having high priority, another one having low priority. How can you say? By seeing the advantages and disadvantages. Okay, here hydrocarbon bases suffers with the disadvantage, that is flammable. Flammable. Due to this property, flammable property means able to produce a fire upon subjected to little stresses. For example, this is the lungs. Now, friends, tell me, lungs having more pressures because to exhale the air, so it having a more pressure. Now you inhale the hydrocarbons. What happen here? There is a high pressures. Due to the high pressure, the hydrocarbons will cause the will give the burner sensation, means it cause the irritation to the membrane. That's why hydrocarbon propellants are never recommended for inhalation purpose. Why? Because of its flammable property. Two times asked question, which propellants are not recommended in inhalation aerosols? That is hydrocarbons. Why? Because of flammability. Due to flammable property, it is not used for inhalation purpose. So once you inhale, what happens? So in lungs, there is a high pressure is there. Due to the high pressure, it be subjected to some stresses, thereby it will cause the burning sensation to the mucous membrane, and also cause the highly irritation. Okay, that's why it is not recommended for inhalation purpose. Next, fluorinated hydrocarbons. Okay, just some hydrogens are replaced with the fluorine atom, then we get the fluorinated hydrocarbon. Friends, remember, fluorinated hydrocarbons are not directly prepared. First you prepare hydrocarbon, next in these hydrocarbons few hydrogens are replaced with the fluorine, then only we get fluorinated hydrocarbons. Upon joining the fluorine, what is the advantage? That is non-flammable. Okay, it cannot produce the fire, it cannot produce the irritation to the mucous membranes of the lungs. That's why this is most preferable for inhalation purpose and also topical purpose, whereas hydrocarbons are preferable only for topical purpose but not for inhalation purpose due to their disadvantage, that is flammable property. Okay, next, that's out of these two, liquefied and compressed, you give the priority to liquefied gas. That's which strike off. Next, out of hydrocarbons and fluorinated hydrocarbons, you give priority to fluorinated hydrocarbons. You can strike off the hydrocarbon. This is the priority of propellants in inhalation aerosols. Okay, fluorinated hydrocarbons are non-flammable. Okay, next, sir, how could you know, sir, it is a flammable or non-flammable? Once randomly I am giving one aerosol product to you, and I am asking, tell me, here in this product there is a propellant is there which is flammable or non-flammable. How could you know? That can be determined by the flammability test. Okay, every stage you have to evaluate the properties. Okay, that's why here I want to evaluate flammability, whether the propellant is flammable or non-flammable using flammability test. Here in industry they will perform flammability test to choose a propellant. Okay, that's why while selecting a propellant, they must perform one spray pattern test, another flammability test. By performing the spray pattern test, we can know whether the propellant maintained constant pressure or not. By performing flammability test, we can know whether the propellant is flammable or non-flammable. So, what is this flammability test? Observe, friends, here. This is the flame extinction test. First one is the flame extinction test. So here, observe, same here, aerosol product. Okay, just you take, this is a candle, flame of the candle. Once you open the aerosol valve, just you press the aero activator for 15 to 20 seconds. Immediately the liquid strike the flame. Here the liquid strike the paper, but here the liquid strike the flame. So once it is a product is flammable, what happens? So it can spread around the candle. How much distance it can spread around the candle? The distance only decide their flammability. For example, here observe, if the flame spread at a distance of up to 20 centimeter, a circle, you imagine like a circle. So what is the radius of that circle? 20 centimeter. If the flame is spread up to 20 centimeter from the candle, then it is called as a non-flammable product. If it is spread up to 45 centimeter around the candle, called as a combustible product. If it is spread above the 45 centimeter, then it is called as flammable. That's why how much distance the flame can spread. The distance only decide the flammability of this product. Okay. So for example, if the propellant is flammable, then you can observe the extension of the flame. Extension means spreading. Extension of flame around the candle more than 45 centimeter. If this propellant is combustible, then it can spread up to 45 centimeter around the candle. Next, if it is non-flammable, just it can spread up to 20 centimeter around the candle. That's why the name itself indicates a flame extension test. Test used to measure extension of flame, spreading of flame from candle. Okay, that's why is a test used to measure the extension of flame from candle. Okay, if it is 20 centimeter non-flammable, 45 centimeter combustible, greater than 45 centimeter flammable. And next one is the flash point method. This is most important. Here you remember three important points. One is what is the definition for flash point? Second, what is the instrument used to measure the flash point? Third one is what is the how could you say based on flash point, how could you say whether it is a flammable or combustible or non-flammable? For this you observe. So you take the aerosol product, next but aerosol product it containing vapor. Okay, that's why you cannot directly open this container. If once you try to open this container, okay, it will be burst out. It will cause environmental hazard like your pressure cooker. So while it is in cooking position, you can try to open the cooker. No, why? Because that inside the container there is a more and more amount of pressure is there. That's why here also same concept here applied. Here more vapor is present. That's why we can't directly open the container. Okay, so flammability test. This flash point test is performed only for product but not container. Why? Because if we increase in flash point test, you increase the temperature. Once you increase the temperature inside the container, what happens? The entire propellant converted to vapor. Thereby the pressure will be increase. At a particular instant, the container will be burst out. That's why to avoid this, first of all, here what is the problem behind the what is the problem? Why you are not opening the container? Because of pressure. How can you? Pressure means pressure is due to the gas. First of all, you convert gas to liquid. How can you convert gas to liquid? You first observe in cold compression method. Observe here gas is converted to liquid. How? By chilling the product at temperature minus 30 degree Fahrenheit or minus 40 degree Fahrenheit. To pour the liquefied gas into the container, you maintain temperature minus 30 degree Fahrenheit or minus 40 degree Fahrenheit. To remove the product from container also maintain same temperature. In some textbook they mentioned is minus 25 degree Fahrenheit also. Friends, here minus 30 degree or minus 40 degree Celsius. Is it wrong or correct? Yes, it's absolutely wrong. Absolutely wrong. Because in aerosols, every time they will mention temperature in Fahrenheit. Okay, I will correct it. Okay, that's why it's minus 30 degree Fahrenheit or minus 40 degree Fahrenheit. This is not a Celsius, it is a Fahrenheit. Okay, why? Because it is an ancient system. Okay, next up, the vapor is completely converted to liquid. Next, this liquid will be poured into the cup shaped apparatus. Like this is a teacup, like a teacup. That's why open teacup or closed teacup, open. That's what it is called as tag open cup apparatus. What do you call it as tag? This liquid will be poured into the container. The liquid will be tagged with the container. Which container? Open cup container. That's what is called as a tag. Tagging means placing. Place the liquid in open cup. That's what is called as tag open cup apparatus. Next, it is a liquid state. Now I am increasing the temperature slowly. So if we slightly increase the temperature, what happens? Some amount of a liquid aerosol product will be converted to vapor. Upon continuous increasing the temperature, what happened? Entire liquid aerosol product converted to vapor. Any further rise in temperature, what happened? The vapor will catch the fire. The vapors will burn. Burning is called as ignition. That can be observed in the form of bright light on the surface. Okay, fire nothing but bright light. Okay, that's why. So the temperature at which, so this is the last aroma. The temperature at which the aerosol product must ignite. Ignite means vapor becomes burned. Okay, so the temperature at which the vapors of aerosol product must ignite is known as flash point. Okay, once again, friends, flash point is the temperature at which the vapors of aerosol product must ignite. Okay, so definition is completed. Which instrument used to measure the flash point? Tag, open, cup apparatus. Okay, so 2 points are completed. So in the flash point method, first take the aerosol product container, next chill the aerosol product. Upon chilling, vapors converted to liquid, liquid poured into cup, next slightly raise the temperature, liquid converted to vapor. Any further increase the temperature, vapors prone to burning. The burning will be observed in the form of like a bright light, observed within fraction of second. That is called as flash. That's the temperature is called as flash point. The temperature at which we observe the fire on the surface of the container, the temperature is called as flash point or fire point. Okay. Next. For example, any product that having the flash point, this is the flash point, and this is the flammability. Any product having the flash point less than 100 degree Fahrenheit means you can observe the fire below 100 degree Fahrenheit, then this product is called as flammable. If it is 100 degree Fahrenheit to 300 degree Fahrenheit, then it is called as combustible. Combustible means first the smoke will come, after that we can observe the fire, combustible. Next, if it is greater than 300 degree Fahrenheit, means the fire can be observed after 300 degree Fahrenheit, then it is called as non-flammable. Once I will say the flammability of the product immediately. Once I say the flash point of the product, immediately you can say whether it is a flammable or combustible or non-flammable. These numericals are not that much important. Never they will ask these numericals. But explanation purpose, I am taking these numericals. Okay. Any product having flash point means fire can be observed below 100 degree Fahrenheit called as flammable product. 100 to 300 degree Fahrenheit called as combustible product. Greater than 300 degree Fahrenheit called as non-flammable product. For example, petroleum, the flash point of petroleum is minus 40 degree Fahrenheit. Means minus 40 degree means less than 100. That's what is a flammable. Kerosene, 250 degree Fahrenheit, as it is a combustible. Wood, that is 450 degree Fahrenheit, that is a non-flammable. Okay, that's once I say, I will tell the flash point, immediately you can say flammability of that product. Okay, then this flammability test is completed. Next up. So already I told you, liquid phase containing propellant or mixture of propellants. Okay. So example for this hydrocarbons completed. Next, fluorinated hydrocarbons example, trichloro, monofluoromethane, difluoromethane, because methane means a CH4. This is called as hydrocarbon. Instead of 4 hydrogen atoms, the 4 hydrogen atoms replaced with the 3 chlorines and 1 fluorine. That's what is called as trichloro, monofluoromethane. Next, difluoromethane. Next, ethane means C2H5. Instead of 5 hydrogens are replaced with 2 chlorine, dichloro, tetrafluoroethane. Next, difluoroethane. These are the examples for fluorinated hydrocarbons. Here you are observing. First, you take the hydrocarbons. Next, some hydrogens are replaced with fluorine and chlorine. Okay. Then next. So in some cases, we use in liquid phase we use propellant or mixture of propellants. Okay, whether the mixture containing hydrocarbons or fluorinated hydrocarbons or compressed gases. How could you know? For example, I am randomly giving the one aerosol product to you, and I am asking, tell me which propellant is present in this product. Because all propellants cannot exert equal pressure. Okay, so pressure is the unique property of that propellant. That's why. So which propellant is present? How could you know? That is how that can be evaluated by the using infrared spectroscopy or gas chromatography. Propellants in the aerosol product can be identified by using infrared spectroscopy or gas chromatography. Because some cases manufacturers to earn the money, they will mention, so propane is present, okay. So for example, propane is very cheap, propane is very costly, that's why they mentioned it is propane is present in this product, okay. But in reality, in the product, which propellant is present, sometimes they will take butane because it is less costly, that's why sometimes it will add the butane. That's why it is a duty of quality control officers to know whether the propellant which is mentioned on the label exactly present in the product or not. How would you know? That is by using either infrared spectroscopy or gas chromatography. These all are evaluation tests, okay. First, which particle size 2 micron, 3 micron, 4 micron. How could you evaluate? By using cascade impactor or light scatter decay. Second, whether the product containing moisture or not. How could you measure? That is by using gas chromatography or carbon feature titration. Next, whether the product maintain constant pressure or not maintain constant pressure, spray pattern test. Whether the propellant is flammable or non-flammable, detected by flammability test. Next, in the given mixture, which propellants are present, that is denoted, identified by infrared spectroscopy and gas chromatography. Okay, that's why in the propellants, how many evaluation tests completed? 1, identification. 2, identification. 2, check the pressure maintained constant or not. Third, flammability. Okay. Next, with this propellant completed. Okay. Next, nomenclature of fluorinated hydrocarbons. Fluorinated hydrocarbon means it containing fluorine, hydrogen, and carbon. That's why my target to know how many fluorines are there, how many hydrogens are there, how many carbons are there. In addition to chlorine, bromine, whatever it may be, I don't want to know how many chlorines are there, how many bromines are there. My target is to estimate how many fluorines are there, how many hydrogens are there, how many carbons are there. Okay, that's why. First, tell me what is the chemical name of this product. That is, you may start with chlorine or fluorine. Okay, dichloro tetrafluoroethane. Once again, dichloro tetrafluoroethane. But if you go and ask in chemical store, please give me dichloro tetrafluoroethane, means immediately they will simply give the smile. It is out of stock because they don't know the chemical structure. That's why you want to ask the name which is present on label. Okay, that is. So this is a nomenclature. This is a chemical name simplified. Simplification means nomenclature. The chemical name is called as nomenclature. The nomenclature of fluorinated hydrocarbons can be simplified by taking 3 digits. By taking 3 digits. Okay. Why, sir, you are taking 3 digits to represent fluorine, to represent hydrogen, to represent carbon. That's why fluorine, hydrogen, carbon. That's why you take the 3 digits means to represent fluorines, hydrogens, and carbons. Okay, I don't want how many fluorines are there. Okay, I want only fluorine, how many, hydrogens, how many, carbons, how many. Okay, that's why. So nomenclature of fluorine hydrocarbons can be simplified by taking 3 digits. Okay, so the first digit from right. First digit from right. You can start from right side, not left side. Okay. The first digit from right indicates number of fluorine atoms. Number of fluorine atoms. Friends, observe here how many fluorines are there? 1, 2, 3, 4. That's right, fluor. Completed. Second, the second digit from right. Second digit from right indicates number of hydrogens plus 1. Number of hydrogens plus 1. Okay, that's why number of hydrogens. How many? Here there is no hydrogens. 0 hydrogens. That's why 0 plus 1. That is equal to 1. Yes, this is the one. Okay. Next, third digit from right indicates number of carbons minus 1. How many carbons are there? 1, 2. 2 carbons. 2 minus 1. That is equal to 1. Yes, third digit is 1. Okay. Because here 1 is added. Next here 1 is removed. That's why C minus 1 plus H plus 1 plus fluorine. That's why what is the remaining? 1, 1 cancelled. The remaining is carbon, hydrogen, and fluorine. Okay, that's why the first digit indicates number of fluorine atoms. Second digit indicates number of hydrogen atoms plus 1. Third digit indicates number of carbon atoms minus 1. Okay, that's why you go and ask in chemical store, please give me propellant 114. Don't say 114. Okay, that is wrong statement. You have to say 114 because every digit indicates a specific atom. That's why propellant 114. Okay, next, Then here you convert. So this is the trichloromonofluoromethane. That's why trichloromonofluoromethane. That's why I don't want the nomenclature. I want in digits, propellant. Okay. Now tell me how many fluorines are there? From right, first digit from right indicates. First digit from right indicates number of fluorine atoms. Number of fluorine atoms. That's why here. So fluorine atoms, how many? One. First digit completed. Second digit. Number of hydrogens plus one. Here hydrogens are zero. Zero plus one. Third digit. Number of carbons minus one. Here carbons are one. One minus one, zero. That's why there is no value once you place the zero before the digits. That's why sometimes they cannot take the zero. For methane derivative, they always indicates with the two digits. Why, sir? Because the third digit becomes zero. Methane means one carbon, one minus one is a zero. Okay, that's why one carbon is one minus one, zero. That's why sometimes they cannot take this zero. Okay, because there is no value. Next, dichloro, P, propellant. Next, how many fluorines? Two. How many hydrogens? Zero. Zero plus one, one. Number of carbons? One. One minus one, zero. Okay, next, this one. P, propellant. Number of fluorines? Number of fluorines? Four. That's why four. Number of hydrogens? Zero. Zero plus one, one. Number of carbons? Two. Two minus one, one. That's what is called as propellant. One, one, four. Next, this one. Propellant. This is a trifluoroethane. Trifluoroethane. I don't want the nomenclature. I want only digits. Number of fluorine atoms, 3. First digit completed. Second, hydrogens. 3 hydrogens. 3 plus 1, 4. Next, carbon atoms. 3. 3 minus 1, 1. That's what is a 1, 4, 3. 1, 4. The propellant 1, 4, 3. Okay, likewise, you can give the digits. Okay, so first digit from right. You always remember first digit from right. Number of fluorines. Second digit from right. Number of hydrogens plus 1. Third digit from right. Number of carbons minus 1. Next. Here. First nomenclature. 1, 2, 3, 4. Trifluoro, dichloro, ethane. Or you can start with chlorine also. Dichloro, trifluoroethane. Okay. So tell me, first of all, convert it into digits. First number of fluorines. How many? 1, 2, 3, 4. Yes, 4 completed. Number of hydrogens, 0. 0 plus 1. 0 plus 1. 1. Yes, 1 is completed. Next, number of carbons, 2. 2 minus 1. 2 minus 1. 2 minus 1. 1. Yes, it is also completed. But what is the difference between these two compounds? This is also dichlorotetrafluoroethane. This is also dichlorotetrafluoroethane. That's why molecular weight is same, but differ in spatial arrangement. Different spatial arrangement of atom called as isomers. Isomers. Tell me, is it isomers exhibit same properties? No, because this first compound exhibit a properties. It's entirely different from properties exhibited by second compound. Okay, only one property is same, that is molecular weight. These two molecular weight is same, but properties are entirely different. The melting point of this first compound not equal to second compound. Boiling point of first compound not equal to second compound. That's why. Now tell me, is it two compounds exhibit same pressure? No. Then how can you denote isomers? How can you denote isomers? That is, observe here. On the first carbon, there is a fluorine. These attached atoms are called as valencies. Attached atoms are called as valencies. The 3 valencies means 3 attached atoms. The 3 valencies on both carbons, observe this one and this one, is entirely same. The 3 valencies on both carbons are entirely same. Then it is called as symmetric molecule. Observe, this is a mirror images. So left side is entirely same as the top right side. That's why symmetric molecule. Symmetric molecules only denoted with the number. But here you observe. How many valencies are same? Only one valency. Fluorine. Next, chlorine. Here fluorine. Here fluorine. That's only one valency is matching. Okay. If one valency, next compound you observe. 1 matching. 2 matching. Here 3 matching, but here 2 valencies are matching. That's why if 1 or 2 valencies are same on both carbons, then these compounds are called as asymmetric. asymmetric molecules. Asymmetric molecules are denoted with the number followed by letter A. Letter A. Once again, if the three valency means attached atom. If the three valencies on both carbons are entirely same, then the molecule is called as symmetric molecule, which is denoted with only on number. Whereas if one valency or two valencies on both carbons are same, then it is called as asymmetric molecule, denoted with the number followed by letter A. A abbreviation asymmetric molecule. Okay, next you observe the third molecule, fourth molecule. Here the carbon containing fluorine, but second carbon containing fluorine. Tell me, is any one at least one valence is matching? No, that's why these are called. This is called as highly asymmetric molecule. Highly asymmetric molecule. Highly asymmetric molecule. Highly asymmetric molecules are denoted with a number followed by letter. Denoted with number followed by letter. How can you denote the numbers already completed? Then sometimes you can observe number followed by letter A, number followed by letter B. So in which case you use the word A, that is in asymmetric molecule. What is asymmetric molecule? If one or two valencies on both carbons are same, called as asymmetric molecule, denoted with the number followed by letter A. Okay. Now here you observe how many fluorines are there? 1, 2, 3, 4, 5. That's why number of fluorines completed. How many hydrogens are there? 0. 0 plus 1, 1 completed. Carbons 2. 2 minus 1, 1 completed. Then if you use only number, then immediately you decide it is a symmetric molecule. Tell me, friends, is it a symmetric molecule? No. Why? Because only two valences are matching. If three valences are matching, then only it is called as symmetry, which is denoted only on number. That's what it is here. Next, here three valences are entirely different. That's what is called as highly asymmetric molecule, denoted with the number followed by letter B. First, tell me how many fluorines? 1, 2, 3. 3 is completed. Number of hydrogens 0. 0 plus 1, 1 completed. Carbons 2. 2 minus 1, 1 completed. Then is it, if you use only 113, then immediately you decide it's a symmetric. Now tell me, by observing the structure, is it a symmetric? No. Asymmetric? No. Highly asymmetric. Highly asymmetric molecules denoted with the letter B. That's why A, comma, B represents degree of asymmetry. A is simply asymmetry. B is highly asymmetry. That's why A, comma, B denotes degree of asymmetry. Next, observe this is a cyclic compound. What is the name? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Octafluoro. Octafluoro. Meth, eth, prop, but. Octafluoro, cyclobutane. Octafluoro, cyclobutane. I don't want that much a bigger word. I don't want that name, chemical name. I want only in digits. First P propellant. First you convert digits. 1. How many fluorines? 1, 2, 3, 4, 5, 6, 7, 8. 8. That's here. This is wrong. Okay. This is not 4. This is 8. This is 8. So I will correct it. Okay. This is 8. Because how many fluorines are there? 1, 2, 3, 4, 5, 6, 7, 8. Okay. 2, 4, 4, 8. 8. Next number of hydrogens. Number of hydrogens 0. 0 plus 1, 1. Completed. Number of carbons 1, 2, 3, 4. 4 minus 1, 3. That's why it is a 3. That's why. So this is a propellant 318. Propellant 318. Okay. Number of fluorines 8. Number of hydrogen 0. 0 plus 1, 1. Number of carbons 4. 4 minus 1, 3. 318. But it is a cyclic compound. How can you represent it is a cyclic compound? That is denoted with the letter C. Letter C. That's why it is a 318. Cyclic compounds can be denoted with the letter C followed by number. Followed by number. Actually, here letter A, comma B always observed after the digits, but C always observed before the digits. Okay, and the C abbreviation is cyclic compound. Cyclic compounds always denoted with the letter C followed by the number. Okay, next. So I will correct this thing and I will place, I will send the material. So which does not containing this wrong one. Okay, next. I will correct it. Okay. Next one is, don't bother. Next one is the okay. Cyclic compound denoted with C. C always present before the digits. Whereas A comma B always denotes always present after the number. A comma B indicates degree of asymmetry, whereas C indicates cyclic compounds. Next, you observe the last compound. This is the meth, eth, prop, bute. Okay. So 1, 2, 3, 4. This is called as a butane, but it containing unsaturated. The specificity here is asymmetry. Here is cyclic. Here is unsaturations. Okay, that's what is called as 1, 3 butadiene. Butadiene. 1, 3 butadiene. I don't want name. I want digits. First, tell me how many fluorines are there? 0. Yes, 0. Next, how many hydrogens? 1, 2, 3, 4, 5, 6. 6 plus 1, 7. Okay, completed. Next, number of carbons? 1, 2, 3, 4. 4 minus 1, 3. That's why 3 is completed. But how can you denote the number of unsaturations? Number of unsaturation. How many double bonds or how many triple bonds are present? That is denoted with the digit. Okay. Already I told you, to represent fluorine, hydrogen, carbon, you take 3 digits only. If you unfortunately observe fourth digit, immediately you decide it is an unsaturated compound. It is unsaturated compound. Now tell me, in this compound, how many unsaturations are there? Just 2. That's why I'm indicating it is 2. That's why this fourth digit from right. Right, indicates the number of unsaturations, either double bonds or triple bonds. Okay, unsaturation. Okay, friends, this is the nomenclature. They never ask in GPAT examination, but it will be repeatedly asking in a NIPER examination. Okay, first, represent chemical name in digits. Second, represent symmetry, asymmetry. Third, represent cyclic specificity. Fourth one, represent unsaturation. Okay, so digits, symmetry, asymmetry, highly asymmetry, cyclic, unsaturated. Okay, with this nomenclature of fluorinated hydrocarbons completed. Next, third basic component is valves. Okay, so how many valves are there? Okay, what is valve? Component containing orifice, means small hole, that are activator, stem, ferrule, valve housing, dip tube. The activator is made up of polyethylene or polypropylene, simply plastic. Okay, so every in industry, activators are always made up of polyethylene or polypropylene. Stem is made up of nylon or delene. Chemically, nylon is polyamide. Chemically, delene is polyacetal. Okay, next, ferrule made up of aluminum or stainless steel. Okay, because in previous question paper they are asking, so in the aerosol preparation, in aerosol manufacturing, the gasket is made up of, the stem is made up of, the dip tube is made up of. That's why material of construction is important. Okay, next, valve housing. Valve housing or valve body. Why it is called valve housing, valve body? Because stem is enclosed in this chamber. That's what is called as is a house or body for stem valve. Okay, which is made up of nylon or delene. Okay, stem is made up of nylon or delene. Their house or body also made up of nylon or delene. These two components are made up of same material. Next, another important point regarding the valve housing is, friends, observe, this is the chamber. First of all, what happened? The aerosol product will be moved from dip tube and enter into chamber where it can be stored. Here stored. Well, that's why it is a guest house for the liquid and also stem. Upon pressing the activator, what happened? The product which is present in this chamber only entirely ejected out. That's why this chamber with a specific volume. For example, if it is marked as 100 microliter, means it can accommodate only 100 microliter of liquid. Upon pressing, 100 liquid only ejected. Okay, any valve housing which is having specific capacity or specific volume marked on this valve housing, then it is called as metered valve. Okay, actually metered valve is simply a valve housing with a specific capacity. It means on the label they will mention the volume of that chamber, volume of that valve housing. Once they mention, then that much product only stored, that much product only ejected out upon pressing the activator. Each activation will deliver 100 microliter. Then this specificity, so the specificity shown by any valve housing is known as a metered valve. Valve which can deliver accurate quantity of medicaments. That's what is called as metered valve. It is not a specific component. So this valve housing sometimes called as metered valve. In which time? That is, it having specific volume or capacity. Okay, that's why metered valve is a valve housing with specific volume. Next, but here on label they mentioned 100 microliter. Friends, don't consider is 100 microliter exactly ejected out. No, some allowance must be accepted. Some variation is accepted. That is called as acceptance. Okay, valve delivery. Which valve? Metered valve delivery and acceptance of difference. Okay, because accurately 100 microliter cannot be ejected out. Some variation will be there. Some difference. Okay, how much difference? If on this chamber, this chamber, they marked it as 54 microliter or less, then how much variation is acceptable upon pressing? No need to accurately 54 microliter will be ejected. Okay, just some deviation is acceptable. Or add 54 plus 15. 54 plus 15. How much? 9. Next, 6. Okay, 69 microliter. Remove 15 from this 54. How much? Remove this 15 from 54. Reduce. That is how much? 44, 30, 29. 13. Okay, 39 microliter. Yes. So some allowances, some variation is accepted by the FDA. That is, so if on label they mentioned 54 microliter, not exactly 54 microliter can be delivered per activation, each activation. Okay, some variation is acceptable. That is 39 microliter to 69 microliter. In between will be accepted. That is called as a percentage variation accepted. For example, on the container, if they labeled as 55 to 200 microliter, then how much variation is accepted? Plus or minus 10%. For example, you consider here on label they marked as 100 microliter. 100 microliter means that lies in between 55 to 100. That's why 55 to 100. How much variation is acceptable? Plus or minus 10. Add plus 10 and remove minus 10. Tell me, plus 10 means 110, minus 10 means 90. That's why. So that this chamber accommodate 100 microliter means not accurately 100 microliter. It can occupy either 110 microliter or 90 microliter. Upon activation, it can deliver either 190 to 110 microliter in between. Okay, that's why this allowance, this variation is accepted. That's why this is 2019 question. So this is the metered value delivery in microliter and the percentage of variation accepted. Okay, if the valve housing having the capacity 54 or less, then variation accepted is plus or minus 15%. If the valve housing marked as 55 or 200, the variation accepted is plus or minus 10%. Okay, next one is dip tube. Dip tube is made up of polyethylene or polypropylene. Observe this activator and the dip tube made up of same material. Stem and their valve housing made up of same material. But only one valve made up of metal. Is the ferrule. The remaining all are made up of plastic. Okay, That's why activate or dip same material, stem and their body, same material, ferrule made up of metal. Okay. Next, inside this chamber, there is a gasket made up of moon iron or neoprene rubber. Okay. Next, spring. Spring is made up of stainless steel, which containing iron. Stainless steel is an alloy of iron, chromium, nickel. Iron, chromium, nickel. Okay. With this, the valves also completed. In valves, material of construction is important. Material of construction is important. Last heading, that is testing of aerosols. Testing of aerosol, also called as evaluation of aerosol, that is already completed. Okay, that is according to Department of Transportation. So how can you perform the evaluation test? That all guidelines given by the Department of Transportation. Okay, that is first one is leakage test. How can you perform the leakage test? Friends, observe. Take a beaker. Next, add the water. Next, raise the temperature 130 degrees Fahrenheit. You know that in a cycle tube, how could you know? How can you detect the leakage in the cycle tube? So how can you detect the puncture in the cycle tube? Because inside the cycle tube there is a air is present. Yes, this inside the container also there is a vapor is present. If any leakage, what happens? The vapor will be expelled out in the form of air bubbles. Once air bubbles will be observed, then we can say that there is a leakage in the container. This is a simple technique. Okay. So in leakage test, place the aerosol container in a water bath, maintain it 130 degrees Fahrenheit, and observe any formation of air bubbles. If air bubbles formed, there is a presence of leakage. Next, you start from introduction part. Okay, introduction part. That is, first one is importance of particle size. So how can you measure the particle size? How can you evaluate the particle size? Cascade impactor, light scatter, decay. First, next. In the containers, what is the evaluation test you are performing? All containers are sensitive moisture. How can you determine the moisture content? Carlo-Fischer titration, gas chromatography. Next, propellants. In propellants, so we use a propellant or mixture of propellants. Okay. So which propellant is present? How much quantity is present? How could you identify? That is infrared spectroscopy, gas chromatography. Next, how could you identify whether the propellant maintain constant pressure or does not maintain constant pressure? Spray pattern test. How could you know whether the propellant is flammable or non-flammable? That is flammability test. That's why that are sequentially written here. Leakage test, measurement of particle size, determination of moisture content, identification of propellant, spray pattern test, flammability. Okay, so this is the evaluation. So who told you to perform this evaluation test and who given the procedures to perform this evaluation test? That is Department of Transportation. Next, determination of foam stability. How can you determine the foam stability? First, you have to know what is foam. Gas enclosed in a liquid film. Gas uniformly distributed in liquid. Okay, what is the lifetime of foam? Okay, that lifetime of foam ranges from few seconds to few minutes. It is difficult to measure the time required to break the foam. Break the foam. But then how can you evaluate how much time it will be stable? How much time it will be stable? Okay, so measurement of time is difficult, but we know that as the viscosity of this liquid film increases, means thickness of this liquid film increases. Thickness of this liquid film increases. What happens? Time required to break the foam also increases. If the viscosity of this liquid film decreases, then the viscosity of the if it is decreases, what happens? The time required to break the foam also decreases. That's why the time required to break the foam depends on viscosity of the liquid. Viscosity means thickness. That's why measurement of time required to break the foam is difficult, but measurement of viscosity of the liquid is possible. That's why determination of foam stability means measurement of viscosity of the liquid. How can you measure the viscosity of the liquid? By using rotational viscometer. The basic viscometers are, one is capillary viscometer, also called as Aerosols viscometer. Second one is falling spear viscometers, also called as Poplar viscometer. These two are used to measure the viscosity of only Newtonian fluid. What are Newtonian fluid? As the force is applied increases, and the proportionally viscosity also changes. Okay. Okay, that's why. So Aerosols viscometer and capillary viscometer, falling speed viscometer, Hopper viscometer, use it to measure the viscosity of only Newtonian fluids. Okay, Newtonian fluids. Okay, whose viscosity is proportional to the applied force. Okay, as the force applied increases, if we apply 1 unit of force, there is a decrease in 1 unit of viscosity. To apply 2 units of force, there is a decrease in 2 units of viscosity. If that type of relation is maintained by any liquid called as Newtonian fluid, whose viscosity measured by using capillary viscometer, another name is Aerosols. Falling speed viscometer, another name is Doppler viscometer. Okay, next. So examples are monophasic liquids. Monophasic liquids, that is water, glycerin, castor oil. One liquid is called as a monophasic liquid. Their viscosity measured by using capillary or Aerosols, falling speed, capillary or Doppler. Okay, but this foam is not a monophasic liquid, it is a biphasic. Observe, gas in a liquid. Suspension means solid in a liquid. That's why this biphasic dosage forms not comes under Newtonian fluids, it comes under non-Newtonian fluid. Why? Because non-Newtonian fluids. Why? Because the applied force not proportional to the change in viscosity. If we apply 1 unit of force, there is a rise in 4 units of, there is a decrease in 4 units of viscosity. If we apply 2 units of force, there is a decrease in, there is a decrease in 8 units of viscosity. If they apply 4 units of force, there is a decrease in 20 units of viscosity. Is it a proportion? No. Such type of relation exhibited by any liquid called as non-Newtonian fluid, whose viscosity is measured by using either cup and bob viscometer or cone and plate viscometer. Cup and bob and cone and plate viscometers are commonly used to determine the viscosity of non-Newtonian fluids. Non-Newtonian fluids. Example, biphasic dosage forms. Okay. So as dispersion, aerosol is a dispersion which containing two phases. That's what comes under non-Newtonian fluid, whose viscosity calculated by using cup and bob and cone and plate. So in cup and bob and cone and plate, okay, what happened? One component will be existed in rotation state, another component is stationary. Here observe, instead of here bob, there is a cone, there is a cup, here plate. Actually, these two instrumentally same, but differ in the analysis of sample volume. So if one droplet, two droplet viscosity measured by using cone and plate. If 1 ml, 2 ml viscosity, that 1 ml, 2 ml cannot be held by plate. That's why you take a cup. That's why these are two are instrumentally same, but differ only how much volume how much volume of liquid viscosity is measuring. Okay, next. So in these two cup and bob and cone and plate, one component will be in rotation. For example, here observe bob and cup. Cup is rotated, bob is stationary. Whereas here bob is rotated, cup is stationary. Stationary. Okay, that's why. So out of two component, one component is exist in rotational state. That's why they are called as rotational viscometers. Rotational viscometer. Instead of mentioning cup and bob, cone and plate, just you say the rotational viscometer, which can measure the viscosity of non-Newtonian fluid. Example for non-Newtonian fluids are biphasic dosage form. Yes, aerosol is also a biphasic dosage form. Okay. Next, so if the cup in rotation, how could I identify? If the cup is in rotation, then it is named as a Q type of rotational viscometer. Q type of rotational viscometer, where cup in rotation, bob is stationary. Example, McMichael viscometer. Only one instrument is available in current market that belongs to Q, where the cup in rotation, bob is stationary. Okay. Next, shell type. In shell type, bob in rotation, cup is stationary. Example, Stromer viscometer, Hockey roto viscometer, Brookfield viscometer. These viscometers are used to calculate viscosity of only non-Newtonian fluids. Foam is a non-Newtonian fluid because it containing gas and liquid. Okay. Next. So here the Brookfield viscometer having one specificity. Actually, these are all used to measure the viscosity of non-Newtonian fluids. Exception Brookfield. By using Brookfield, we can measure the viscosity of both the Newtonian and the non-Newtonian fluids also. Non-Newtonian fluids. This is the importance of Brookfield viscometer. Even it belongs to rotational viscometer. Rotational viscometer used to calculate the viscosity of non-Newtonian fluids, but exception is Brookfield. Brookfield viscometer can measure the viscosity of both Newtonian and non-Newtonian fluids. That's when in every industry, for Newtonian fluids and for non-Newtonian fluids, they cannot take the So different instrument, they take only Brookfield. By using Brookfield, we can measure the viscosity of both Newtonian and also non-Newtonian fluid. This is about instruments used to measure the viscosity. Determination of foam stability means measurement of viscosity of the liquid. How can you measure? By using rotational viscometer. Why could you say rotational viscometer? Out of two component, one component in rotation, another component in stationary. With this, evaluation is completed. Evaluation is completed. Previous question papers. In case of aerosol testing, valve delivering acceptance criteria for a volume of 54 microliter or less is, already I told you friends. So this is the valve housing. On this valve housing, they marked as 54 microliter or less. Friends, means it can accommodate only a volume of 54 microliter of liquid or less. Okay, then tell me, upon pressing, is it essentially it can deliver accurately 54 microliter? No, some allowance must be allowed by the DOT. What is DOT? Department of Transportation. Okay, so how much allowance? That is plus or minus 15%. 15. Okay, already it is completed here. That's why if the volume of this valve housing is 54 to or less, then the percentage variation accepted is plus or minus 15%. Okay, next, that's why answer is plus or minus 15%. Next, 2019, which of the following oxide is not used for achieving amber color? Already I told you friends, amber color means brown color. Brown color. Which salt will produce the brown color? Which oxide, which metal oxide produce brown color? That is ferric oxide. Ferric oxide. But they are asking not produce, not. Okay. Now tell me, in the given option, we know that only iron. Iron always produce brown color. Brown color means amber color. Then next, that's why you can remove this one. Next, you know the cobalt also. Cobalt produce blue color. Already I told you cobalt oxide produce blue color. Okay. Next, I don't know the magnesium oxide. I don't know the carbon, but you have to eliminate the options. Okay. We exactly know cobalt always produce blue color. They are also asking not used for achieving amber color. That's why I'm selecting the cobalt. I don't want the manganese. I don't want to know carbon. I know only two options. One is iron. Iron always produce amber color. Another one is cobalt. Cobalt always produce blue color. Yes. So they are saying which metal cannot produce amber color means cobalt cannot produce amber color, because I know 100% confident that is cobalt produce blue color. Okay. Likewise, you have to eliminate the option. It is impossible to know the everything in pharmacy. That's why you have to apply your knowledge. Okay. You have to apply your thinking. That is called as aptitude. Okay. They want to check your aptitude, how you are responding. Okay. That's why likewise you have to screen the options also. Okay. Next one is GPAT 2018 and GPAT 2012. Containers used for aerosols should withstand a pressure of, friends, you know that. So aerosol container means immediately you remember metals only, because that only withstand higher pressure. That is 140 to 180 pounds per square inch, gauge at 130 degree Fahrenheit. Next, dot is performed for, where you heard the dot, Department of Transportation. It is entirely related with the aerosols. Okay, that's the dot is performed for which of the following aerosols. Okay, because all guidelines to perform evaluation tests of aerosol is given by dot, Department of Transportation. Next, NIPER 2009. Imagine that you are developing an aerosol formulation, drug formulation, to deliver the drugs into conducting areas. Friends, tell me, conducting areas means a middle chair. Which, who will sit in middle chair? That is 5 to 10 micron particles. In introduction, I completed. That's why 5 to 10 micron. Okay. Likewise, these are the previous question papers. In any examination, they will ask any bit only from my material. Okay. So that much confidence I will give you. Okay. Friends, with this, the previous question papers also completed. Okay. Next, once again, I will repeat what are the headings. First, aerosol. So what is aerosol? Introduction. In the introduction, definition, first point. Second, importance of particle size. Third point, determination of particle size. Next, basic aerosol technology. In basic aerosol technology, basic components. What are the basic components? One is container. Second, propellant. Third one is valves. Okay, that's the container. What is the important point? Pressure withstanding by the container. Which pressure is important? Metal withstanding pressure. Next, so always either metal or glass sensitive to moisture. Whether moisture is present or not, how can you determine? By Carl feature titration or gas chromatography. Next, propellants. So propellants, what is the function of propellant? Simply to supply the pressure. So it is available in two types. What is the difference? How it can be filled into the container, either in liquid state or in gaseous state. So gas is converted to liquid by using temperature minus 30 degree Fahrenheit or minus 40 degree Fahrenheit. It is called as cold filling method. Okay. So out of these two, one having more importance, that is liquefied gas. Why? It maintains constant pressure. Next, how would you know? By performing spray pattern test. Next, liquefied gas is again classified into hydrocarbons and fluorinated hydrocarbons. Okay, but out of two products, one having the more important, another having less importance. That depends on advantages and disadvantages. Hydrocarbon disadvantage, flammable. Petroleum is a mixture of hydrocarbon, that is a flammable. That's why due to this flammable property, not used for inhalation purpose. It is only absorbed in deodorants, topical purpose. Topical purpose only we use. Okay, whereas fluorinated hydrocarbons is non-flammable, used for both topical and inhalation. Next, so how could you know whether it is a flammable or non-flammable? By performing flammability test. Next, in some cases we use a propellant and propellants. In propellants mixture, which propellant is present? How could you identify? That is infrared spectroscopy, gas chromatography. Here, important is the flash point. What is the definition for flash point? Next, nomenclature. First digit from right, number of fluorine. Second digit from right, number of hydrogens plus 1. Third digit from right, number of carbons minus 1. Next, so symmetric molecule, asymmetric molecule, cyclic compound, unsaturated compound. Valves, third component valves. Material of construction. Next, testing of aerosol. These are the evaluation tests. Okay. Next. So previous question papers. Okay. Thank you, friends. Today I taken 10 minutes more. Okay. So, friends, thank you for listening patiently and peacefully my class. Okay. I will assure you. So every minute of every valuable minute I utilized and it will be converted into bits. Okay. Just you follow my material. Okay. Next. So myself and Nagarjuna sir, pharmacology lecturer. So myself and Nagarjuna sir efficiently and successfully running the Hyderabad Academy from past 10 years. Okay. So online and also offline. Okay. So every batch, actually the coaching time is 60 days. Every day there is a 4 hours, minimum 4 hours. Okay, within 60 days we can complete the GPAT syllabus. For every 10 days we conduct the online examination, and after completion of the batch, we provide the online materials. Okay, that's why it's entirely now due to the COVID effect, we are running online coaching. Okay. Next, if anybody interested, please contact to this number. If you have any doubts regarding pharmaceutics, so you may please freely contact to this mail ID venkatraosutics@gmail.com and contact number 8340192252. And this number also having the WhatsApp. This is my WhatsApp number also. So I think, friends, this chapter will be helpful for your GPAT examination and NIPER examination and many government recruitment examination. Okay, so you have to learn. First of all, you have to focus on basics. Okay, basics. Once you know the basics, then you can easily understand the many standard textbooks. Okay, many of them asking the standard textbooks. Okay, first one is for surgicals, biological products. You follow the tutorial pharmacy by Cooper and Guns and Bentley's textbook of pharmaceutics. Second, For suppositories, you may follow Industrial Pharmacy by Lackman, okay, and also Pharmaceutics by Ansel and Alton. Next, for capsules, just you follow the Industrial Pharmacy by Lackman. Next, for aerosols, same, you follow the Industrial Pharmacy by Lackman. Okay, that is enough. Lackman is enough for aerosols, suppositories, capsules. Okay. Thank you, friends. And my sincere thanks to the Honorable Educational Minister of Andhra Pradesh and Vice Chancellors of JNTU Anantapuram and JNTU Kakinada, and also SP Satyanarayan sir. He is the academic planning director, and Padmanav Reddy sir. He is the director of RIPA, Raghavendra Institute of Pharmaceutical Education and Research. Because of their profound effects on the GPAT, online GPAT conduction. Okay, they are successfully running this online GPAT academy, and also they are every time thinking about the pharmacy profession and can try to boost up the pharmacy profession and try to increase the knowledge of pharmacists. Okay, thank you, sir. Thank you so much. With this, the current session is completed.